system-based research efforts for understanding healthy child development. And its research on environmental risk and promotive factors has fostered a more comprehensive understanding of what is necessary to improve the cognitive and social emotional welfare of children. He has published numerous research articles in 12 books, most recently The Transactional Model of Development, How Children and Context Shape Each Other, and Regulatory Processes in the Development of Behavior Problems, Biological, Behavioral, and Social Ecological Interactions, with Cheryl Olson. Among his honors are the Distinguished Scientific Contributions Award from the Society for Research in Child Development and the J. Stanley Hall Award from the Developmental Division of the American Psychological Association. He's a former president of the Society for Research in Child Development, the Developmental Division of the American Psychological Association, and the International Society for Infant Studies. He currently has reached level 285 of Candy Civic. Please join me in welcoming Dr. Sameroff.
Thank you for that nice introduction. Actually, I'm up to level 293. And I'm hoping to crack 300 by New Year's. I don't know if I want to thank you guys for dragging me out of retirement. With retirement, you have to figure out new things to do. You have to re-examine your whole personality to find out what to do. And I figured out what I really like is solving problems. So what I do most of the day is do the New York Times crossword puzzle and my video games. So, in any case, I was invited to give a talk partially because I'm going to talk about this lectureship in developmental theory that's starting in developmental psychology. And when that was set up, a call went out for nominations for people who would be a lecturer. And then a big list showed up. And in examining the list, one of the questions was, what was the theory of the person who was on the list? And it sort of became not clear, but interesting that a lot of people on the list were very famous scientists because they were collecting a lot of interesting data, but didn't necessarily have a theory about that. So to distinguish people who are doing theories versus those who are collecting data is part of the challenge in some way. And so when I asked the committee to solve the problem, they said, why don't you solve the problem? I said, no, I'm retired, but anyway. So I thought I'd come up and talk about this a little. Psychology is really a fascinating field. We're the greatest of all the scientists. Because, you know, other scientists, eventually, biologists, say, well, we can see a cell, and we can see what's in the cell, and then you can see the molecules, and then you can see the parts of the molecules. So there's a hope at some point they're going to see what actually life is all about. Physicists say, okay, we saw the atom. Well, there's things in the atom, there's electrons and protons, but actually there's things in the electrons and protons. So there's kind of an infinite regress in some way, but each level they find something interesting to look at. Psychologists, in my mind, and it will never see what we're studying. We're going to see parts of the brain, we're going to see neurons, we're going to see areas lighting up, but most of our research is saying, what are people thinking? We have a theory of mind. We're getting much better at studying that in infants, but our science is deciding to have a theory of mind. What goes on in people's minds? We can watch their behavior, but thinking about what they're thinking about gets more and more complicated. And there may not be an infinite regress in saying, let's get down to the basic ideas, because the basic ideas that people use are combinations of a whole variety of things. And we'll talk about that a little. So then I'm going to talk about what's a theory. I'm going to talk about metaphors and models. And then somebody named Sameroff came up with this unified theory. So I thought I'd mention that as an example of a theory. And then we can sort of discuss what this is about. So the developmental question that most of us are concerned about, in part or in little pieces, is you start with babies, and they end up being successful adults, like everyone in this room. How do we get to be this way? What are the processes that intervene? What went on? And it's very simple to understand. And I owe this slide to Al Bandura, who used it for one of his complex theories. And actually, it's 200 systems that control your blood pressure. So if your blood pressure, which is one number, is controlled by 200 systems, you can imagine what the mind is controlled by. So trying to do something with this, we sort of make a distinction about trying to find out among all of this thing, what are the regularities? So statistics gets more and more sophisticated looking at our data, and what statistics is about, you got all this noise, all this numbers all over the place, and what's the sense in it? Where's the signal? What's the meaning in all that? So theorists seem to try to do the same thing, that you look at all the noise and say, how can I explain it? A good example is Galileo in the physical realm, because there were a bunch of phenomena, like dropping a rock from a tower, or shooting a cannonball, or rolling a ball down a ramp. Now, just to look at it, people before Galileo said, well, these are three completely different situations. But he was able to show that using the same equation, he can explain all three of those. They were just part of a falling body equation. So that's part of what we want to do. Some prior examples of development is Freud, who came up, for example, with the notion of overdetermined behavior. So someone goes and kicks a dog, and the behaviorist would say, oh, a person was angry at the dog. But it turned out that this guy's mother had yelled at him an hour before. So the idea that something that happened to you before can influence what you're doing now indicated to Freud that there was an unconscious, there was something going on in the mind that was over-determining it. It wasn't simply you saw a dog and kicked it, but there were other things that came to the fore. Piaget, much more recently, things like the water glass problem, where the kid gives the wrong answer. And we as adults say, what the hell's going on with this kid? They're obviously stupid. And Freud says, well, actually, they're looking at it in a different way than we are. But different perspectives are going to produce different answers. And a current example is an adult attachment theory or attachment theory, where you do an interview asking people about their childhood. And the person is saying, my mother was wonderful, she treated me with kindness and respect, and in the meantime the person's crying. You say, why are they talking about these happy thoughts and they're crying? So obviously something else is going on, and that theory has a particular view on that. But these would be kinds of examples. So a scientific theory is generally considered to be a well-confirmed explanation. It's testable, that you can do experiments to test it. It's falsifiable, we'll talk about that in a little more, is that if you test it and it doesn't come out as you expected or predicted, then we have to throw out the theory. You falsify it. And very important now, a lot of discussions on theory in the literature, that theories are always backed by evidence. And most of this came about from the religious right, that all these people who are arguing there's no such thing as evolution, for example. So they take little things and they throw it at and say, look, you found a contradiction, therefore the theory's wrong. But the counter theories generally don't have that kind of evidential background. So scientists now are saying this is what a theory is, that you're predicting that UFOs are coming probably is not a true case, but some emphasis. So we want to explain nature, we want to predict events. Theory tells us what to look for when you're looking at a problem, tells us what our data mean. So they do a lot of good things. Hypotheses are not theories. Most of our studies are based on hypotheses. They're empirically testable, but they can serve different theories. For example, if you're studying some measure comparing boys and girls, and you find a difference, is that a theory? Actually, it's not, because that can serve a whole variety of theories. One theory is, well, boys are biologically different than girls. Another theory would be boys are socialized different than girls. And now with all our self-psychology, identity issues, that may be a different identity than girls. And now we have so many other identities. But hypotheses are great, but they're just not at the theoretical level. And now we have things like exploratory studies where there are no hypotheses and no theories. And we have to figure out a category for them, even though they can provide data. The strength of a scientific theory is based on the diversity of phenomena it can explain. The more you can explain, the better the theory. Elegance and simplicity. The idea you're looking at all that noise we talked about and making it simple with a few little equations. E equals mc squared, for example. A unifying explanation for a set of verified proven factors. Predictions in new areas. You have a theory that came from one area, and you look at a new area and say, well, I expect to find the same relationships. When theories first, not when they first came about, when scientists first began to think about theories as theories, they tried to make them mostly mathematical. They had to be a set of propositions with axioms, with corollaries, and you'd be testing these various things. And if you couldn't lay it out that way, it didn't qualify as a theory. But modern times, modern times started probably when I was retired. The scientific theories are moving away from that kind of model and becoming more like models rather than propositions. This is kind of a mapping of what the world looks like. It's representative, and sometimes can be used a model as a simplification of a complicated theory. Some idea about things changing a bit. Now, the falsifiability was associated with this guy, Karl Popper, who was in the early 1930s, 40s, who defined science for everybody. And his big thing was, you never could confirm a theory because you have to test all the instances, all the possibilities to prove that your theory is correct. But somebody may have another possibility you didn't test, so you'll never know. But if you find one time that it wasn't confirmed, that you got a negative conclusion, then you had to throw the theory out. So you couldn't confirm it, but you could falsify it. So everybody had to set up their theories in very clear statements and very clear logical sequences so that you could falsify it. You could have a test that said it wasn't true. Well, early limits were, Newton had a theory of gravitation, and they discovered a planet called Uranus. And Uranus, all the planets were supposed to move in this direction in appropriate ways, and Uranus wasn't doing it. So I said, aha, it falsified the theory. Newton was wrong. But it turned out there was another planet that was affecting Uranus. So it wasn't that the theory was wrong, they just didn't have all the facts. Well, people saying, this falsifiability notion, maybe we shouldn't throw out a theory just because you found something that didn't fit. Modern times, we have, in physics, you probably are aware there's this thing called string theory. And most physicists are really buying into us. They think it's the most wonderful thing since bread, if you thought that was a wonderful thing. And it turns out there's no way of testing it. That it's an elegant mathematical theory where all these things, conjectures, fit into this very clear model, but there's no way of testing it. In fact, part of the theory says, well, if it doesn't work this way in this universe, there are alternate universes. So we're just one universe among many. So you're saying, well, that's such an exciting theory in physics, but it's not falsifiable. So these are alternative approaches to saying this notion of falsifiability is not so great as a criterion. So in modern times, most theories are not discarded after negative results. We tweak. We search for a workaround. And that's based more on models than theories. Now, in the history of science, Karl Popper was concerned with the logic of science, how all these things fit together, as I've been describing, with logical positivism, and you remember what that was, and a notion of cumulative progress. That is, there's science, whatever, psychology or chemistry, and every one of you now is adding to the science. So the advancement of science is fact 1, fact 2, fact 3, fact 4. And as I mentioned, the role of the scientist is to falsify, not confirm. In about 1960s, there's a guy named Thomas Kuhn who came out with a book called The Structure of Scientific Revolutions. And he was more concerned with how scientists actually did science. And when he came up with the idea, or he was a historian, so we actually told historical stories, that theory science does not go by steps. That there's a period in time where everybody believed a particular theory. And there's more facts, and the more facts don't confirm the theory, but sort of don't fit the theory. So you take the theory and you stretch it this way, then you take the theory and you add a corollary, or you add a footnote, and at some point the theory is so unwieldy, it really doesn't look like this idea of simplicity. And then somebody else comes in and says, hey, you know, I think there's a much better explanation for all of this stuff. And it turns out the much better explanation explains all the anomalies together with what came before in a new theory that kind of fits the data. So this is the idea of more of a revolution than evolution. So you're going along, and all of a sudden you reach a point that you have to turn the whole thing around. And in physics, the shift from Newtonian physics to quantum physics started by Einstein and then the quantum mechanic people. So normal science is what Kuhn called what most of us do. You do compare boys and girls, black boys with black girls, and white boys with white girls, young kids with old kids. You work out all these parameters, but you're just grinding out information that somebody else is going to take and say, oh, all that data you collected, really we have to throw it out because we have a whole new conception. And part of our work, which is interesting, is that while you're working, you come out with simple hypotheses and you start noticing things that you didn't notice before. So in learning theory, they had rats running down alleys, and what you were training them to do was you made them hungry or thirsty, and then they had to learn if you turn right, you got food, if you turn left, you get water. You have to go through these mazes. And what people sort of noticed was when you put the rat in, these were rats that were starved. The first thing they did wasn't run down the alley, they would look around. They would say, oh, what's going on here? And people regarded that as noise. I mean, that's what you have to get through before you can do the experiment. Later, we began to realize these rats are actually not motivated by learning to drive, they're motivated more by getting information. And the first thing you do is check the scene before you then start trying to satisfy your hunger and food needs, which was the learning theory idea, or drive reduction idea. So there are contradictions you find in doing the work, excuse me, that change what you do. Now I titled this talk Paranoid and Bewildered. I was at an SRCD meeting and walked by Sheldon White. I'm kind of drying out here. That's what happens when you retire, you don't talk so much. And I said, Sheldon, what are you doing these days? He said, well, I'm studying paranoid psychology. I said, well, what the hell is that? He said, well, I study people who have a theory that explains everything. I said, uh-oh. I left him. Later I saw the paper, and it was called Paranoid versus Bewildered. And the contrast was, bewildered psychologists are ones who collect data, and you say, well, I'm waiting for the data to speak to me. Tell me what the truth is. You sort of look at your numbers. As opposed to paranoid psychologists who have a theory when they come in, and when you look at the facts, you can tell which are the good facts and which are the bad facts. Obviously, the good ones are the ones that fit your theory. So there's a fascinating study by a guy named Ian Mitroff. When we landed on the moon, the Apollo landings, there were 52 scientists that were given pieces of rock that we brought back from the moon landings. And NASA was interested in seeing what they would get from these rocks, what kind of science. And this guy Mitroff was a sociologist, and he went and interviewed all of these guys. And it turned out there were some guys who had very clear ideas about what the rocks mean, what the moon means, the history of the moon, where it came from. And there were other guys who sort of were just kind of looking at the rocks, putting it in their spectrographs, seeing what kind of chemical composition they were. And the guys who had these very extensive theories, it turns out most scientists felt that these guys would never change their minds. In other words, it didn't matter if you took, one quote, the whole moon, took it apart, put it together in his backyard, and shoved it up his, he would never change his idea about what the moon was. So this idea, there was another dimension in the study. One was they had people who were assistant professors, associate professors, full professors, and Nobel Prize winners. And interestingly, the two dimensions kind of correlated. That the more likely you were to have a theory that people felt you would never change it, no matter what the facts were, the more likely you were to be a Nobel Prize winner. And the most open-minded people were the assistant professors. So this kind of issue about how psychologists actually do their work. So paranoia is a mental illness in which a delusional belief is the sole or most prominent feature. The delusional belief that you have a theory that explains everything. Scientists work within a conceptual paradigm that influences the ways in which they see data. You'll go to great lengths to defend your paradigm against falsification by the addition of ad hoc hypotheses, which I mentioned. And changing a paradigm is very difficult. It requires an individual scientist to break with his or her peers. So one of the paradigm shifts that a number of our older faculty lived through was the shift from behaviorism to cognitive science. And part of it was the rise in developmental psychology of Piaget. So we had all these guys who were talking about stimuli, responses, reinforcement, conditioning. And then this new theory comes out, and they're talking about accommodation, assimilation, adaptation. And the old guys were saying, I don't understand any of this. It must be wrong. When I took learning theory in graduate school, there was a famous learning theorist named Neil Miller teaching my graduate course. And he said, look, students, my theory probably has a less than 50% chance of being correct. But in order to criticize it, you have to learn it. I was in his last class. I was the last person who had to learn that. And it turned out you didn't have to learn it, because after the shift into this, quote, cognitive revolution, I'm skipping over a lot of stuff here, all that learning theory data, you could mostly just throw it out. All this data on running rats, making turn right, turn left, what were the schedules of reinforcement, really had very little to do with our new conception of how the mind works. So those kind of shifts require, unfortunately, I'm putting it positively, it requires new scientists, but it does require the old guys to die off. There are very few learning theorists still around, and most of them are around in training animals to do drug tests, which is very useful, or fly rocket ships. Skinner did with his pigeons. So this idea, and if you look at the history of science, there are things that you remember in learning in chemistry in high school. There was a phlogiston theory explaining about combustion, and then it turned out that the phlogiston theory had all these little patches that was eventually found to be too weighty or too heavy and thrown out. So changing the way people think is very hard, and we psychologists, we study that kind of stuff. So that affects scientists in the same way. So where do our theories come from? How do we get a new theory? Well, imagination. Now, who would say a thing like that? Imagination is more important than knowledge. Knowledge is limited to all we now know, while imagination embraces all there ever will be to know. So here's this Einstein guy. Obviously, he should know about this stuff because he did make some major contributions to our understanding of the universe. But one of the ways of structuring imagination is through metaphor. Robert Frost was a famous poet a long time ago. I don't know if they still teach Robert Frost, but anyway, he was giving a lecture and he said, I've wanted in late years to go further and further in making metaphor the whole of thinking. We still ask students in college to think, but we seldom tell them what thinking means. We seldom tell them that it's just putting this and that together. It's just saying one thing in terms of another. So metaphor is as if statements, we're saying. This acts as if it were that. So current times, we've got this guy Lakoff, who's gotten extremely important in our understanding of metaphor. And his work and his research and his colleagues have argued that understanding truth, and we were talking about this understanding through a particular theory, depends on your conceptual system, the way you think about the world. Minds work through metaphors. Abstract thought is largely metaphorical. So metaphors are grounded in everyday experience. They're embodied in the nervous system, which is really the more recent thing. They're unavoidable, ubiquitous, and mostly unconscious. So the way we behave to each other, the way we behave in the world, it affects politics, Republicans versus Democrats, advertising, everyday interactions. The way we interact with the world, with each other, is influenced by our metaphors, which may largely be not subject to our consciousness at the time. When we were graduate students in the 60s, that's 50 years ago. That's 2 generations, 3 generations. Us old guys have been around a long time. But at that time, we were very much concerned with fighting behavioralism. We started out as a new developmentalist, especially being influenced by constructivism, by Piaget, and the new mentalism. We have to say, well, what is the difference between our theories and your theories? So a lot of people talked about root metaphors. And the root metaphors that were most involved were 4: formism, mechanism, organism, and contextualism. So these root metaphors were statements like the universe is formistic, and that was because the universe is like ideals. It's mechanistic because the universe operates like a machine. It's organismic because the universe works like a living cell. Or it's contextualist in that the universe operates like historical events. Now these, the middle 2 were the most important at that time. And the formism ideal kind of thing was found mostly in the idea that things like causality, things like spatial things are entities in the real world out there. I mean, they're independent of your human existence. It comes from Plato and things. And it's transformed like genes. Genes are things that are indivisible, which control different aspects of the world. So they're isolated from experience, they're isolated from context, they're isolated from development. And still in language, and Chomsky's versions of language, there were certain kind of cores, kernels, that reflected this idea. The mechanistic one was the one that was most dominant, and the idea that the world operates like a machine. What does that mean? If we study the machine and look at its parts, once we find its parts, that'll explain how the world operates. Like if you take a motor, you take it apart, you got a cylinder rod, these different pieces, and you look at them and you put them together, that explains what a motor is. Well, that was a nice idea, and a very simple one, and pushed the idea that we keep looking at parts. We look at the habits people have, we look at different behaviors. But then this organismic idea came in. And the organismic idea was that the universe acts as if it were a living cell. Now, the interesting thing about living cells, where with a mechanistic theory, if you're thinking about motivation, for example, you say, what gets the machine going? So it turned out you need to have something outside to get the machine going. You had to put gas in it, you had to do something else. With the organismic model, the living cell, you don't worry what gets it going, because it's alive, it's going. You just accept that as a basic principle. And the interesting thing about the living cell is holistic. It operates as a whole. Well, what does that mean? Well, two things. One, if we reduce it to the parts, we can't because the thing died. The other thing is you can substitute the parts. There's molecules going through all the time, which is changing the whole organization of the cell, not the organization, they're changing the parts of the cell, but the cell is still the same, it still has the same function. So this holistic notion that people are wholes, the mind is whole, cultures is whole, came to dominate in some way. And then the lifespan people came along, and they said, well, you guys are forgetting this contextualism. And what that means is that they kind of mislabeled things when they started. They say, well, you organismic people, the cell is kind of preordained. That is, that it's teleological and that its end is in its beginnings, meaning if you look at the genes in some way, that'll predict how the cell will turn out. So it's kind of determined. Where we lifespan people, we look at people's lives and we see they're changing all the time. They're doing different things all the time. So they must be more influenced by context. That all the things that are happening around you are changing your ideas, changing your feelings, changing what you're doing. So the contextualist perspective actually is part of how the living cell works. The living cell, as we understand it now, through all this molecular biology which has come out, is completely influenced by the cells around it, the different parts around it. So the determinism is kind of dropped out of the model. So we have to look at things now in some way as being influenced by all the things around them, but still maintaining some kind of continuity, which is what the cell does. Maintains itself in the face of all this change. So as I mentioned, in lifespan developmental, and then, for example, quantum physics. Now we're getting very, psychology always wanted to be based on these hard scientists. You know, we couldn't say something unless it was like physicists talk or biologists talk. So what are physicists dealing with now, physicists? Quantum physics, and I don't know if you just read, I think 3 days ago, there was an article about the spook elements. But there's this idea that every particle is represented everywhere in the universe. It's over here, no, it's over there, no, it's over here. And the way they think about that is there's not particles, but there's fields, and the fields permeate the whole universe in some sense. So they were able to get a particle over here, they touched it, and some particle over there did something. So this idea of spooky relationships, that everything's connected, kind of supports our notion that when we think about psychology, we can think more of fields and networks. So general systems theory has been a model that we've used frequently to keep those ideas about what's in a cell that we should be thinking about when we do our science. Using the organism metaphor, you identify the wholes, and then you can see what are the parts of the cell, and more importantly, not importantly, but it turns out every part is made up of parts. So you have an infinite regress. So you have hundreds of parts and wholes. What is the network of relationships? What are the dynamic regulations or constraints? And the developmental system theory is concerned with where did you come from and where is it going. So my 10-minute talk is moving on a little. I'll give you a rough history of how we've been thinking in developmental science. In the 80s through the 1940s, 1880s. When you looked at people and say, why are they different? You say, well, they were different inheritances. In fact, they have phrenology. You can feel the bumps on their head and tell about their personality. They have different instincts. And then 1920s with Watson and following with behaviorism said, well, no, it's not what's inside people, it's what happens to people. It's your reinforcement contingencies, it's your experiences that make a difference. Psychoanalytic theory was very prominent at the same time, saying your personality just isn't built in some way, but your experiences are what change you the way you feel. Then in the 60s and 70s, there was ethology came in. And it turned out that learning theory, which had these general principles that applied to everybody, only applied to the white rat. Because if you looked at different species, you were finding different ideas about learning, different capacities. So your theory had to change. Behavioral genetics came in, cognitive revolution, which was focusing on the way the individual operates on the world rather than the reinforcement histories. And in the 80s and 90s, nurture came back, where we said, okay, yeah, species are different, individuals are different, but things like poverty is a way of organizing reinforcements of things in ways that make people very different. Social ecology, the way different aspects of your life affect you, and getting into now cultural deconstruction. Everybody has a different identity, which is going to, as we've been talking about theories, influence the way they experience their experience. And now we're going back to nature in some way with molecular biology, the new genetics, neuroscience, where we're being able to tap into the brain and do things much more in detail than we were before. So what do you notice here? One is that there's a cycling of explanations. First it's nature, then it's nurture, then it's nature, then it's nurture. Each step is always seen as, you guys were wrong and we're right. However, each step, turns out, leaves most of the variance explained. And that's the crucial test. When you're doing an experiment, how much variance are you explaining? I mean, if you've got a 0.05 difference, it could be 0.0001 of the variance explained. So we have to have models that explain a lot of variance. So this cycling is partly tied to technological advances, our understanding of nature, our understanding of nurture. It's tied to theoretical advances. Is it a linear historical progression, or is it a phenomenon in itself? So if you took the GRE, you may have done a sample question, and the question was, science advances in a blank spiral, in that each new conceptual scheme blank the phenomenon explained by its predecessors and adds to those explanations. So right in the test it says, there's a widening spiral that embraces phenomenon. So that's interesting. The GRE has it, but psychology has that too. Developmental change moves in spirals. And we can think about this in one idea, that it's a helix. Developmental helix means you cycle and you come back to the same thing, but at a higher level. So day-night, you went through the day, you went through the night, you come to a new day, but it's a different day because you had the experiences of the day before. Representations. First you just look at objects, then you can draw pictures of objects, then you can use words to represent the same thing. So you're coming back to the same object, the same thing, but at a more complex level. And even relationships, mother-child relationship becomes peer relationships, becomes romantic relationships. You still have relationships, but as you move up developmentally, they're more complex. Berner, who's one of the heroes of our old-time developmentalists, talked about development as differentiation and integration. It proceeds towards a state of increasing differentiation and hierarchical integration as you move up this helix. So we expect to see things getting more detailed as we learn more about it, but we learn all this stuff, we kind of chunk it in some way. We get a meta theory about that, and we move to a new level. So if we think about the differentiation of nature, when we're doing research, first we notice there are behavioral differences. Look, people are different, they behave differently. So I said, oh no, that's not what's going on. We have neurological difference, that's important. Well, it's not the neurology, it's actually the biochemical changes in the neurology. But really, those are genetic differences in the way the genes are operating. And now we know they're epigenetic differences. So our understanding of what the individual is about keeps differentiating. And nurture, we used to say way back in the 1800s, all that was important was that your mother loved you. And if she didn't, you turned out badly. But then we had reinforcement learning theory, which said, well, mother love is really a whole bunch of reinforcement contingencies. That's what it's about. Then people say, well, actually, reinforcement contingencies in different social situations are different. That's what it's all about. So then we got into social ecologies, where we could look at each context and say, well, those are all different kinds of experiences. And now with social deconstruction, it's adding the meaning systems, the people's meaning systems, keep imposing on how nature, how our experience is interpreted. So we can think about this change from nature to nurture as part of this differentiation. Psychological theories are kind of, one idea, restricted by real science. That is, if you want to have a good psychological theory, it has to be linear causal. You can have equations, this leads to this, to this, to this. And we had examples through history. Clark Hull was one of our learning theorists who explained all of behavior in his particular equation. Kurt Lewin was a little simpler, and he was a famous social psychologist that behavior is a function of a person and environment, so he's bringing the two elements in. And now we have a new guy, James Heckman, who was a Nobel Prize winner in economics, and this is his current theory of development. I to the p is equal to beta p, xp, etc., etc. But once we get into real science, everything is part of a system. We don't have these linear kind of chains anymore. So physics has given us the uncertainty principle that no matter what you do, actually you can never find a certain point, that there's always something that's outside the system. And that makes things a little looser. And then this field theory that says, well, you can't find a particular thing because it's all over. So that gets more comfortable. Biology, we had the Genome Project, was a very linear idea. We're going to find all the genes, and then we're going to find the gene that affects schizophrenia, cancer. So we're going to cure all the diseases of the world by this Genome Project. And as you all know, the Genome Project was a failure. On the other hand, it was a great success for us in that came molecular genetics that said genes don't go from here to there, they go from here to here. And they affect this gene, which affects that gene, which affects these genes, which are affected by those genes. So you had all these complex chains eventually getting to something. So to simplify it and say it explains 1% of the variance, it's nothing to do with what actually goes on, because there are like hundreds of thousands of interactions in between. So these have really freed developmental psychology to be much more open and inclusive in our kinds of theories. I was going to talk about a particular theory, the unified theory of development, which captured all of these. And so my own vision was, how do you put all we know about development into one theory? And the point I was leading up to is that if you're looking for something that, say, E equals mc squared, you won't find it. But if you're looking at a mapping kind of saying, what are all the things that go into development, then this theory kind of does it from my perspective. So I'm going to run through it in half a second. I have to find out how you get a unified theory, so I talked to this guy here. And this was a child development article in 2010. And I said that if you want a unified theory of development, there were 4 things you had to have included in it. One was a theory of individuals, how individuals change over time, because that's kind of our focus. You had to have a theory of context, because we're all influenced by environments. You had to have a regulation model for understanding how the individual interacts, transacts, whatever, with the context. And then finally, you have to have a representation model, because all of these things are represented in the way we think about children, the way children think about parents, the way parents think about children, the way cultures think about children, the way children think about cultures. They're all entwined at some level of representation. So I'm not going to do that. Just to give you the final. This is with representation. You have to read the article. But what I proposed there was interesting, was 4 models. I said, these are the 4 models, but I left it open. I said, you know, whenever I gave a talk, I said, if someone has 3 models or 7 models, I'll be happy to discuss that. And it took a couple of years, but then someone said, hey, you forgot about evolution. And so I added that to the model. In the sense that this whole system, that our developmental system, is changing over time. So it's not just people changing over time, but the world changes and these kinds of things. So we have 5 models now. So bottom line is we try to look at this complexity. We got Heckman's theory. Well, the projector's not showing it. He's got a lot of little equations. And there's a little sidelight here. A guy wrote an article, should the history of science be X-rated? That you shouldn't teach your students the history of science. Well, why would you want to do that? Well, it's what I said earlier, because most people, most of the time, are going to be collecting data that may ultimately be useless, or at best be the grist for somebody else's mill, who's going to come in and say, you guys got it all wrong. Here's the real way of doing it. But Heckman, we have a lot of people from the outside. So he has a Nobel Prize in economics. Do you think that he must have discovered some new economics theory? That's what gets you a Nobel Prize. No, he worked out a theory for getting unbiased samples for your research studies. Economic prizes are a little different than the other Nobel Prizes. They were set up separately, but that's a separate history. In any case, this, if you could see the numbers on my PowerPoint slide, would be an equation that explains development. This is the simple model I came up with. And I'll leave you with another quote from Robert Frost, or coming to the end, we seldom tell students it is just putting this and that together. It is just saying one thing in terms of another, which we said before. But he concludes with, to tell them is to set their feet on the first rung of a ladder, the top of which sticks through the sky. So hopefully that can be something you guys can do in the future. Thank you.